let's quickly go through. Let's figure out why this is not working. All right, we're going to quickly discuss just hemoglobin dissociation curve. So once this loads, we're just going to take a look at this right here with the hemoglobin oxygen dissociation curve. So when we look at this, set of notes starts right here. And these set of notes are going to explain what happens with the hemoglobin oxygen dissociation curve. Now, an important concept here is that, right, at higher and higher oxygen content in the atmosphere, we top out in our saturation of hemoglobin. So what we're going to see is when we are at 100% or 100 millimeters of partial pressures of oxygen in the atmosphere, we'll be at 99% saturation in our hemoglobin dissociation curve. Meaning that even if we go to, let's say, 110, right down here, right, we can't go beyond 99% saturation. So what it really allows us to do is it allows us to actually live at high levels and at high altitudes. So if you take a look, right, let's imagine that you live in the mountains and there's about 30% less oxygen. So normally we're at 100 PO2, now we go to 70 PO2. If we follow the chart, even at 70 PO2, we should still be close to 94% saturation, meaning that, you know, people that are having 30% less available oxygen are still able to have 94% of their hemoglobin saturated with O2. Now, we also notice that when we look at a deoxygenated system at rest, let's imagine your skeletal muscles. So skeletal muscles at rest are going to have a PO2 in the 40 range. So what happens then? Well, with a PO2 of 40, the blood and the red blood cells leaving that site, that inactive tissue, will still be about 75% saturated here. So when we are at rest, we only give away about 23 to 24% of our available oxygen. This is very important because this is one of the real fundamental reasons why we are and we can do just compressions when somebody is doing CPR. We're assuming that under CPR conditions, there's a lack of blood flow, that the oxygen content that's found in the red blood cells is still high enough for as long as we are able to move the blood, that blood will have oxygen in it. Now, when you take a look right here, right, this sigmoid curve of the O2 dissociation curve means that between about a PO2 of 40 and a PO2 of 20, there's a massive drop. So when we look at a PO2 of 40 in active tissue, about 75% saturation. But let's say that tissue is active. As the tissue becomes more active, like the skeletal muscle, the tissue is going to use more oxygen. The tissue is also going to use and give up more, right? Get more ATP, also carbon dioxide and water is released. What happens is because it's using more oxygen right there, the oxygen content is going to be at a PO2 of 20. Now what we see then is that at a PO2 20 now, only 35% of the hemoglobin will be saturated, meaning that you've given away a lot more oxygen. And it kind of makes sense, right? The more active the tissue, the more oxygen that it requires. And because it requires more oxygen, your red blood cells are going to favor giving away that oxygen to those more active tissues. So when you look at these oxygen dissociation curves right there, again, just fundamental reasons why people can, one, live at high altitudes, because when you look at the difference between 70 to 100, well, maybe 5% saturation difference. So not a big change, and people are able to survive, you know, not at the very tip of like Mount Everest, but near the bottom of Mount Everest. Now, we can cause a shift in the curve. Now, shifting in the curve means that we favor giving blood or giving oxygen away at the same, right, PO2. So what? Well, I want you to think about when you're looking at this, right, low blood pressure, low blood pH, let me phrase that, right? When you have a low blood pH, right here, we can see that as a sign of acidosis. We can see that as a sign of, right, lactic acidosis, diabetic ketoacidosis. It's gonna cause a right shift. So then the normal curve is over here at a PO2 of 40, 75% saturation. If we have a right shift at a PO2 of 40, right, what happens then is that the oxygen and the red blood cells leaving that site is only 50% more saturated. So you've given away a lot more oxygen and, right, at the same amount of oxygen content that we see. So right shifts always favor unloading of oxygen to the tissues. Left shifts always favor oxygen keeping by the red blood cells, so then you can target it for the really, really important tissues like your brain, like your internal organs. So if we take a look at this example, high blood pH over here, we have a left shift. A left shift at 40, again, normal is about 75%, even though it's kind of, right, about 70, 75%. With the left shift, what happens is, right, that PO2 of 40, now we're about 80, 85% saturated. So we're keeping the oxygen primarily for your internal organs and the brain, and we're not gonna give it away as easily at any given PO2s.